So this lesson is going to be on covariance, and it's going to be quite algebraic, quite theoretical. Covariance is another statistic. Currently, we're focusing on bivariate statistics, where we've got two variables. So covariance is the two-variable or multivariable version of the variance. And just like variance measures spread from a mean, so variance measures spread from a mean, and if variance is small, then most of the data is sort of gathered together around the mean with just a few points out here. If the variance is big, then you might still have mu at the same point, but it's more spread out. What covariance measures is the spread from a regression line. Two variables. And the question is, are they close to the regression line, or are they very spread out? So similar to and related to the R value that we saw last lesson. So in the example on the left, covariance is small because the points are close to the line. And the example on the right, covariance is bigger. So there's a lot of analogies that can be made between the variance and the covariance, starting with the definition. So variance of x is defined as the expectation of x minus mu squared. And the covariance of x, cov, of x and y, because it's two variables, is defined as the expectation of x minus the mean of x times y minus the mean of y. So you take all, because obviously your points come in pairs, so for each pair of points you'd work out the mean of all the x values, the mean of all the y values, and you calculate the expectations like that. But it turns out that there's a, just like with the variance, is equal to the expectation of x squared minus the expectation of x all squared. There's a similar simplification we can make for covariance, and it goes like this. I'm going to expand out the brackets. The expectation of xy minus the mean of x times y minus the mean of y times x minus, sorry, it'll be plus mu x mu y. And since expectation can be taken through any linear expression, we get sorry, should be mu y x plus mu x mu y, and then you can take mu x and mu y are just numbers, so you can take them out as factors. So we get that the covariance is given by the expectation of xy, minus mu x times the expectation of y minus, getting equal signs where I'm meant to have minus signs, minus mu y times the expectation of x plus mu x mu y. However, since the expectation of x is equal to mu x, and similarly the expectation of y is equal to mu y, you can probably see what's going to happen here. A lot of this is going to cancel. And we get that the covariance is equal to the expectation of xy minus the expectation of x times the expectation of y minus the expectation of y times the expectation of x plus the expectation of x times the expectation of y. Just using those two single relationships. And obviously we've got expectation of y, they cancel. And there's our definition of covariance. Expectation of xy minus the expectation of x times the expectation of y. This has a useful side effect. Which is to say that if two variables are in x and y are independent, what does that mean? Well, if two variables are independent, then the expectation of xy is equal to the expectation of x times the expectation of y, which means that the covariance would be equal to expectation of xy minus the expectation of x minus the expectation of y. Well, it's going to be 0 because the expectation of xy, if they're independent, is just 0.